Doesn't even have to travel in the air. And a little bit of a sonic boom there. And then you can also do it with other items. Here's a chain of movement. Interesting and scary at the same time. I know it was just a little blip there, but oh, that was Adam CWM.
All right. And as usual, I know what you're thinking. All that's great, but where's the math?
Did I guess it? Did I get it right? Spot on. Let's do some math. Now, in the case of the lab, I know there's an equation here. I guess you could throw math into that. Speed is also frequency times the wavelength. And so if you square both sides, frequency squared, lambda squared is equal to the tangent over the linear density. You plot, I think, wavelength squared versus tension. And this is why you're plotting wavelength squared versus tension, is the fact that it shows up in this equation. And then from that, from the slope, you should be able to, well, you'll know mu because you calculated that. You should be able to calculate the frequency. And if it's done right, it comes out to about 60 hertz. All right, so let's just do it with the person moving, or the source moving. We'll call this cleverly S for source. And over here, R for receiver. So we give out a sound wave. So the sound wave is moving along, and then and then this object, or the source, is moving at some speed v. We're not going to do a sonic boom here. This is just straight old Doppler effect. So the first wave is here, and let's draw it straighter. First wave, and this is when the second wave is produced. Second wave. So I'm going to let c equal the speed of sound. C is also used for the speed of light, and some textbooks for speed of sound will do v sub s, s for sound, but I'm using s for source, and so that's why I'm going to use c here. So I'm letting c be the speed of sound. So the distance traveled here, this first one, is going to be just how fast the sound is traveling times the period. So period of the source, little subscript there. The period is the time between producing the sound. So the first sound is produced, that wave gets to here. This is when the second wave is produced. So the time difference between producing the first wave and the second wave is t sub s. In the same time period, the source has traveled speed times time. And so the distance between these wave crests, this is what the receiver is going to sense as these waves come in. So this is going to be basically the wavelength that the receiver is going to think. Because it's going to be hit by these two pressure waves. So I know that the wavelength for the receiver gets is just the difference in basically the distance between the two waves, which is CTS minus VTS. I know that speed is equal to frequency times the wavelength, or wavelength times frequency, as I just wrote it. So the wavelength is equal to the speed of sound divided by the frequency. So I can write this as, this is just the speed of sound divided by the frequency that the receiver gets. And that's gonna be equal to the speed of sound minus the speed of the source, how fast the noisemaker is going, times the period of the source. The period and frequency are reciprocals, so this would be equal to the speed of sound minus the speed that the center is going, divided by the frequency from the center. So I got two fractions equal to each other. And I'm gonna get it in a more traditional form. I'm gonna get the frequency that the receiver, basically I'm gonna solve for what is the frequency that the receiver gets. So I'm bringing that up and then bringing this over to the other side. And so this becomes Fs C over C minus V. So we can do a quick plug and chug. So I have a car, produces sound at, we'll just say 400 hertz. Now I didn't say frequency of sound, but you should know from the fact that I have units of hertz that I'm talking about frequency. It is driving towards you. Get out of the road, but it's driving toward you at 30 meters per second, just under 65 miles an hour. What is the frequency you hear? So what's the received frequency? All right, so first off, the car is coming at you. So will you hear a higher frequency or a lower frequency?
Higher.
And so whatever I get, I need to make sure that my answer better be a higher frequency. If it's not, then I got a sign in the wrong place or I completely messed the problem up. So the frequency that's going to be received is 400 hertz, that's what's being sent, times the speed of sound, which is somewhere around 343 meters per second, divided by 343 minus 30. So 400 times 343 over 313. So I'm multiplying 400 by a fraction that's bigger than 1, so I am going to get a higher frequency. If someone would be kind enough to give me a value there, it's going to be 400 something. Feeling good with that. Somewhere around 410.
I got 438.34.
438?
I got that too.
Ah, okay. About a 10% increase, that's the brain request. 438, is that rounded up or down?
I rounded up to 34, or at the end.
Oh, 0.34?
Yeah.
Okay. Units?
Hertz.
I hope so. If this 400 is hertz, this fraction here is unitless because the units cancel out. So hertz. So you're going to hear 438 hertz-ish. Now the car passes you. You jump out of the way just in the nick of time, and it's now driving away from you. How does my equation change?
The speed becomes negative.
Because when we derived our equation right here, the source was heading towards the receiver. And so after he passes, then this becomes 400. So this is toward, and this is away. 343 still on top, over 343 minus negative 30, or plus 30. So 400 over 343 over 373.
So, 367.83 hertz.
Now notice that the average of these two is not the actual speed of the source. So, now let's change it around a little bit. Questions up to here before we change it around a little. All right. So now I have a source and I have a receiver, and this time the receiver is heading towards the source. So it produces a sound, and so the first wave is here, this is the first wave. And the second wave is being produced at this point. Coming at some speed, v. Let me throw in, this is speed of source there. Yeah, probably should put the subscript in there. V sub r. So I need to figure out how much time it's going to take for the receiver to actually hit these 2 points. So if I start timing at this point, let's say that's time is equal to 0 at that first wavefront, and now you're running in this direction as the wave is traveling towards you. So the time it takes between here, so the period that the receiver gets, well, that's how far the receiver travels, and the sound travels at c times tr. This whole distance from here to here, that is how far the sound traveled and the time it takes for the source to create the wave. So that's why this is the period from the source's point of view. And so I have CTR plus VRTR is equal to CTS. So this is how far the sound is traveling from the source's point of view. And in that interim, in that time it takes to do that, the receiver travels that far and the sound travels, the second wave travels that far. So I have C plus VR times TR is equal to CTS. Generally you do these in terms of frequency. So this is C plus VR over the frequency from the receiver is equal to the speed of sound over the frequency from the source. And then putting the more traditional form of FR equals, bringing FR over to the right, this over to the other side. We have FR equals FS, C plus VR over C. It looks a whole lot like the other one, except we got a different sign as they're approaching each other. And I've got the addition on the top there instead of on the bottom, or numerator, denominator for those math people. And so let's do a similar problem here. This time, you're producing a sound at 400 hertz as you sit there, and a car is coming at you at 30 meters per second. What sound do the people in the car hear? Again, the source is still producing 400 hertz, just the only difference is who's actually moving. And so we have the frequency that is received by the car is 400 hertz over, well, this will be speed of sound I did was 430. No, I did 343. So this will be 343 plus 30 over 343, which is 400 times 373 over 343.
So that's 434.99 hertz.
Now, as you let out this high-pitched shrill sound of 400 hertz, the car starts driving away from you. What do they hear now? So this is toward and away. So it's 400. I should be getting a lower frequency because the two objects are getting farther from each other. And so this will be 343 minus 30 over 343, which is 400, times 313 over 343.
365.01.
Notice these do average up to be the source of the frequency of the source. But I have different frequencies here. Depending upon who's moving. And this obviously leaves the last case of, suppose they're both moving. Instead of going through the derivation, I'm just going to combine the two equations that we have there. So the frequency that's caught by the receiver is going to be the frequency of the source. And then my numerator depends upon the movement of the receiver. So this is C plus or minus the speed of the receiver. And the denominator then depends upon the speed of the source. C minus plus speed of source. This is a traditional way of writing it. You got the plus minus and the minus plus. You're just supposed to know which is which. So if they're coming towards each other, if the receiver is moving towards the source, it is the top one. If the source is going towards the receiver, it's the top one. If they're moving away, it's the bottom ones. It's helpful to look at it and, you can go through and try to memorize that part, or you can just go, all right, they're getting closer to each other. Yeah. Ultimately, my answer needs to be bigger. I'm going to get a higher frequency. And just to contrast that, even though it's out of scope for this particular course, but just to contrast it, this is the Doppler shift for sound. If we're dealing with light, the frequency that's received versus the frequency of the source times the square root of 1 minus beta over 1 plus beta, or plus minus depending upon if it's going towards or away, where beta is the speed of the object divided by the speed of light. In this case, there just needs to be relative motion. You're not playing around with, is it the other object moving or are you moving? And when you get to light, you're not worried about that. And so this is the relative speed of the two objects. And C in this case is the speed of light. Anyway, that ends the material for the last test. And Tuesday, I will bring in something that will hopefully be educational. And then Thursday, a week from today, is final test. Oh, no, Tuesday, forgot it. Man, I almost forgot this one. The multiple choice test. You know that thing you took the first day? Yeah, we've covered all the material. It's time to do it again. So multiple choice test. And then after that, something hopefully educational.